Hey guys, welcome back to my channel. This is Varun. So in the previous sessions, we had numerous examples to understand the probability. We had also seen a 5-ball game where we did experiment and calculated the probability of getting several combinations of red and blue balls among a set of 3 red and 2 blue balls. So guys, please check out my previous video on probability, as this session is a continuation to that, and to understand things better, I would really recommend to see that one first. Now let's say that we don't have enough time or resources to conduct such experiments. Can we still find out a way to figure out the respective probabilities without conducting any experiment? We will find out the answer in a while in this session while studying a part in discrete probability distribution known as binomial distribution. So right now what we will do is extend our previous session and find answers to some questions, but this time we will not do the experiment, or in other words, we will not consider number of users playing. Now let's say that we have same number of balls in the back, that is 3 red and 2 blue balls. So what is the probability of getting exactly one red ball? So this should be 3 by 5, because total number of balls are 5 and out of that 3 are red. So this is 0.6. Now what is the probability of getting 2 red balls in 2 trials? So by this mean we are taking the ball out and putting it back. Okay, so this is with replacement. In the first trial we will pick out a ball and then put it back, and the second trial we'll again pick the second ball. So the number of balls in both of the trial remains the same. So guys, if you can remember from the previous session, this condition exactly fits the multiplication rule, where the events are happening one after the other randomly with replacement. So when two events A and B are independent, the probability of both occurring is P, A and B. Got it guys? So this should be PA into PB, which is 3 by 5 into 3 by 5, which is 0.36. Now let's calculate the probability of getting this combination in 4 trials. So by 4 trials will mean this is the first trial, second, third and fourth. So we are taking out each of the balls, putting it back into the same bag and then taking out. So these are 4 trials. So what is the probability of getting a blue ball? That is 2 by 5. Because blue balls are 2 and the rest are red. So by the rule of multiplication, we'll just simply say into 0.6. So this is 0.4 into, which is 0.0864. Now let us find out the probability to get 3 red balls in 4 trials. So 3 red ball in 4 trial mean 1 blue ball and 3 red balls. Okay. So how many combinations we can get out of this? So total 4 combinations. So in this question we need to use both multiplication and addition rule. So we can calculate this by saying probability of event 1 or 2 or 3 or 4, which is equivalent to saying probability of event 1 plus probability of event 2 plus probability of event 3 plus probability of event, and for each event we see that there is a multiplication. So while we expand this, you will get 0.4 into 0.6 into 0.6 into 0.6. So this is for one probability, and identically you will find that we will get the same probabilities for the rest of the combinations also. So we can directly say multiplied by 4 here. So we'll get 0.3456. Now we will calculate the probability of getting 0 red balls, 1 red ball, 2 and 3 and 4 red balls. Okay, so for this there is only one possible combination, which is all blues in all the 4 trials. Now for this there will be possibly 4 combinations, which is, now for 2 red balls there are possibly 6 combinations as we have seen earlier, which are, for 3 red balls also there will be 4 combinations. And for x equals to 4, there will be only one possible combination, which is red, red, red and red. Now as we saw, the probability of getting a blue ball is 2 by 5, which is 0.4, and probability of getting a red ball is 3 by 5, which is 0.6. We will substitute these values here. So probability of getting a blue is 0.4. Then probability of getting one red ball is, and likewise we can calculate for others. Now when you calculate, you'll get these numbers, and now what we'll do is we will compare these values with the values we have got by doing the experiment in the previous session. So guys, this is clearly visible that there is only a slight difference between with experiment and without experiment probabilities, and that is also only due to small iterations done. So if we do some larger number of iterations, it could match real-time results. Now let's move on to binomial distribution. So binomial distribution is a part of discrete probability distribution, and to understand this, we will take an example and see if binomial distribution fits here. So let's say that we are calculating the probability of getting a red ball in one trial. Okay, we don't know that, and we'll define that as P. Now we need to know what is the probability of getting 4 red balls in 4 trials. So it is simple, guys. So P x is equals to 4 is P into P into P into P, which is P raised to power 4. And then what is the probability of getting 3 red balls in 4 trials? It is P x is equals to 3, which is P into P into P into 1 minus P. Okay, because probability of getting red ball is P, probability of getting a blue ball is 1 minus P. And as we have seen that there are 4 possible combinations for getting 3 red balls, so we'll multiply this by 4. So we'll get 4P cube 1 minus P. Now as we have calculated for x equals to 3 and x equals to 4, we can also calculate for the rest of the x values. So it will be, now let's say that we choose a ball n times and replace those in bag every time. So what is the probability that you'll get a red ball r times out of n? So seeing the equation, we can clearly observe that it is NCR P raised to power r 1 minus P n minus r. So guys, this is the equation for binomial distribution which fits here exactly, where NCR is the combination. Now using this equation, we can substitute the values for x and calculate the probability, and you will see that these values will exactly match the table here, such that n equals to number of trials, r is number of success after n trials, and p is the probability of success. Now here are some conditions for binomial distributions, and these all should be met in a problem in order for us to apply the binomial distribution formula. The first one is total number of trials should be n, so rather it should be fixed and not variable. Then each trial should be binary, that is only 2 possible outcomes should be there, that is success or failure. Then the probability of success should be the same in all the trials, and which is denoted by P. So these are the conditions that should be met before we apply fourth point, which is the formula for binomial distribution, which is NCR, where NCR refers to combination formula that we have seen earlier, into P raised to power r into 1 minus P raised to power n minus r, and where r denotes the success in n trials. So now we will see some of the examples where binomial distribution is applicable and differentiate them with taking some scenarios where it is not applicable. So guys, remember, in order for binomial distribution to be applicable, we need to have these 3 conditions met for each problem. So the first example where it is applicable is tossing a coin 20 times to see how many tails occur. So here you can observe that there are only fixed number of trials, that is 20, and tossing a coin means there is either success or failure chances for tails to occur, and the success probability should be same in all the trials. So exactly it is half for heads as well as tails. Now the second example is asking 200 randomly selected people if they are older than 21 or not. So this is again a yes or no problem, and it has fixed number of trials, and success probability is same in all the trials. The third example says drawing 4 red balls from a bag, putting each ball back after drawing it. So this also meets these 3 conditions, which is fixed number of trials should be there. There will be a binary outcome if we are just expecting some colored balls. Then the success probability is also same because we are putting the ball back into the bag. So the number of balls remains same. And there are some examples where binomial distribution is not applicable. So the first one is tossing a coin until head occurs. So it does not have a fixed number of trials. Then the second one is asking 200 randomly selected people how old they are. So there can be multiple answers to this. So there is no binary outcome. Now drawing 4 red balls from a bag, not putting each ball after drawing it. So this means that success probability will not be same for all the trials, because it will alter the number of balls in each trial. Now there is this question which says a student attempts a test with 10 multiple choice questions which has 4 possible options. She doesn't know the correct answers to any of the questions. and just randomly selects one of the 4 options for each one of them. Now we have to find the probability that she would still get 3 questions correct. Now here, if you carefully observe, the total number of trials is fixed, which is 10, and each trial has binary possible outcomes, that is either correct answer or wrong answer, and the probability of success is same across the trials, which is 1 by 4, because total 4 options are there and she has to choose one. So we can safely apply binomial distribution here. So the total number of trials is 10, so n becomes 10, then r is 3 because she needs to get 3 questions correct, and so the formula becomes 10c3 1 by 4 raised to power 3, then 3 by 4 raised to power 7. How did I get this? So this is the formula, if you remember. So if you substitute the values here, you will get this. Now if I expand this, I'll still get 10 factorial by 3 factorial to 7 factorial into 0.25 raised to power 3 and 0.75 raised to power 7. So if you calculate this, you will have 0.25 as the answer, which clearly says that she has 1 over 4 possibilities of getting 3 questions correct out of 10, or 25% chance. So this is all for this session, guys. In the next session, we will extend our thoughts of discrete and work with cumulative probability distributions with examples. We will also see some density functions to expand our knowledge on how various distribution works. Until then, guys, try and revise the concepts taught in the previous sessions, as those are really important and will behave as foundation for upcoming sessions. Also, please let me know how are you finding my content, and kindly subscribe and share it with your friends as well who are an enthusiast on data science, as this channel will be your one stop for anything and everything related to data science. Thank you all for the love and support you are giving me. Please stay healthy. I will meet you soon in the next session. Until then, take care and happy learning.